All right. So if you have very different, you end up with having electronegativity. Somewhat different, you end up at a polar covalent, and pretty much the same or identical, you end up at a non-polar covalent. Yep. Too easy. All right. So that's your general gist of what's going on there. So you have the three different types of bonds. You have ionic, polar, and non-polar covalent, and they all happen to work off the difference in your electronegativity. If you have it heaps different, you're going to end up with ionic. If you have somewhat different, you end up with a polar covalent. If you have pretty identical, you end up with the non-polar. So within the ionic one, so let's scroll down a bit. So let's do a little journey down to here. So in our ionic, all right, so within your ionic compound, okay. So with your ionic compounds, they're generally always going to be metals and non-metals. So if you've got James Saul, get out of here. Can't even get rid of him. All right. So you've got your periodic table. You've got low En on this side. You've got high. Hell yeah. So you got high electronegativity over this end. You got low electronegativity down this end. So because you've got big differences between these two sides, well, it's just zoomed out for me. Because you've got big difference of electronegativity between both sides, it results in you generally always forming. What's going on? Generally always forming ionic compounds. Such as sodium chloride. Because sodium over here, chloride over here. Big difference, you get an ionic compound. If we look at sodium by itself, it has one lone electron on the outside. Look at chloride on the other side. It has 4 electrons on the outside. And chlorine has an electronegativity of 3.16, and sodium has one of 0.93. That's a big difference. Big diff. So because of that, chlorine is super selfish, and he's like, yo, I'm going to steal your electron. And because it steals the electron, it now has more electrons on the outside than what it has, so it becomes a negatively charged. The sodium's like, oh, I lost my electron, but that's okay. I'm really positive about this type of thing, and I'm an optimist. So now the sodium now has a positive charge on it. What happens if we have two different charges on something? They attract to each other. Yep. So when you have different types of charges, we get different charge. Whoa. Just lost everything. What did I do? I don't know. What did I do? Here we go. I think I bumped it with my hand and then I actually got out of whiteboard. There you go. I'm trying. I'm doing my best. Remember, I'm an old. Using technology and yeah. Okay. Thank you. I appreciate it. The pen. Oh, pen's back. Okay, good. All right. Pen's gone. Pen's back. Good. All right. Actually, let's go to green. So if we have big difference, we end up having different charges. and different charge equals attraction. So therefore we get an attraction force here, and then we form a new compound, sodium chloride, which is ionic compound. Generally, ionic compounds are quite strong. So because we've got quite like an electrostatic forces are actually really, really strong. If you just think about the fact that you've got gravity is literally like the whole size of the Earth is pulling stuff towards us. But if you just get like a little magnet, you can pick up a paper clip off a table. So electrostatics between things that are really close together are really, 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 really strong compared to other forces such as gravity. So this is really, really strong. Strong. I think that's a strong attraction between them. So that's firstly kind of how ionic compounds work. Now we'll come back up again to where we have polar covalent. And we're going to take polar covalent on a journey down to here. So I'm just going a little bit to the right of the ionic compound. Can everyone see that? Yep. You got polar covalent compounds. So when we have a polar covalent compound, these ones have a pretty similar difference between them. So there's not heaps of difference like with an ionic, but we still have a bit of a difference between them. So can I find some numbers to be able to show? That will do. Okay, so with the polar covalent, there is still a difference, but it is not as massive as in ionic compounds. This results in uneven sharing of electrons. So when we have an uneven sharing, that's like when you get a Mars bar and you snap it and it's like, I want the bigger half. What's the problem with wanting the bigger half? Well, what does half mean? Exactly. You can't have it. Then it's not a half. But you still are like distributing it between two people, but one half ends up being a little bit bigger. With a polar covalent compound, you're essentially doing that exact same thing. That you are splitting things between, and you have... That's your Mars bar. And then you go and you snap it. So you end up having a bigger half. This one could be 60%, and this one here is 40%. So one of them's going to have slightly more than the other one. And if we were looking at it in terms of like our net and electronegativity, this one here could be our fluorine, and this one here could be our chlorine. This one had an electronegativity of 3.6, and this one is a 3.98. So the fluorine side is a bit stronger, and the little electrons that the chlorine has are going to be driven more that way overall. So it's going to end up having more electrons on this side on average. Than the number of electrons over here, so less on average. So you have more electrons on average over at the fluorine end. You have less on average over at the chlorine end. So that's where we kind of start getting our polar covalent molecules going on. So we have more over this way, you have less over that way. And that means if my fluorine has more electrons, what charge will the fluorine side have? Negative charge, good. So this is going to have what's called a delta charge. That's like a little one. A little bit of neg. And what about the chlorine side? A little bit of positive, good. So it's going to have a bit. So it's not as much of an optimist, but he's still pretty happy about it. So he's happy to have lost a little bit overall. So that's the first part there. And then finally, the next part that we're going to go to is just go to polar or non-polar covalent. So let's go on a magical journey with this funny magical colored pen. And we're going to go down to here. So we're just going to go right of the polar covalent. And we're going to go to the non-polar covalent. So in these ones, we have identical EN between our elements. Resulting in an even distribution of electrons between the atoms. So in this case, we'll just use chlorine again. Got chlorine over here, got chlorine over here. Chlorine had electronegative 3.16. 3.16. And this one is that nice 50-50 split. Which means that we have no charges overall. What happens if we have zero charging? We have neutral. What's a neutral thing not going to attract? Electrons, good. So it's not going to attract any electrons towards it. It's not going to attract any polar things towards it. Anything that has a charge isn't going to be attracted to this. It's just going to hang out by itself. So they're more than happy to just live like that. That's that first part of the basics. We just looked at our bonding spectrum. Let's have a quick look at our shapes of molecules if you want. Or what parts in particular were you guys kind of struggling on and weren't too sure? Yep. Did anyone have trouble with allotropes? That's pretty good. Yep. What about the ionic networks and all that stuff? Yeah. Cool. And the covalent network and the covalent molecular solids? Yep. Cool. Anyone else? Oh, generally. Okay. Cool. Alright, in that case, let's go to that. So the bond strength, was it? Yeah, bond strength. Okay, so that's the dipole, like the different types of bonding. So the intermolecular and intramolecular forces. Cool. Is that Everyone in general, that was the hardest bit. Yep. Yep. Okay, so I'll do that stuff then. All right, I'm going to put a line through it. And pen stopped working again. That's what it likes to do sometimes. Oh, we're back. Go. All right, putting a big solid line underneath all that first stuff. And let's move on to inter and intramolecular. So we're going to look at intermolecular and intramolecular. Intra is what's happening inside of our thing, and then inter is between. So intra is inside the atom or inside the compound. And inter is between molecules. Cool. So when we're looking at these, we have a couple of different ones. So our intra ones are inside the compound, and this is going to be our covalent, ionic, and metallic. So there are three main types there, and I think we're okay with those ones. Now we're going to look at the inter. Oh, why has it moved? And these are main ones that we're going to have is a dipole. We're going to have dispersion forces. And we're going to have hydrogen bonds. Hydrogen bonds are what keeps us alive. It makes life on Earth possible. Which is kind of cool. Okay, so we'll start off with the dipole. So let's do another little subdivision here. Let's make a little box full of dipole magic. Cool. Everyone's following along? Yep. Cool. All right. So, sorry, my foot's just got stuck inside the legs of the chair. Standard. No, I got it out. We're okay. I'm not gonna have to cut it off. Okay, so dipole forces, they occur between the molecules, which are polar. So if you have a polar covalent molecules, then you're going to be getting dipole forces generally acting between them. So this can be things like water, it can be things like hydrochloric acid, or hydrochloride. It can be like that chlorine-fluorine compound I showed before. So these ones result in you having slightly differences of charge overall within your compound. So let's go green for positive. And then we're going to make this part over here red. So we have a little bit of negativity over here. This is the part we don't really like in our classroom. We want a positive learning environment. We have a bit of positivity over here. Oh, what just moved? Oh no, right. Damn it. You just destroyed everything. Oh, you're almost there. Almost fixed it. Alright. And then we're going to just have slightly negative again. And we're going to have slightly positive again. What happens when we have different types of forces or different types of charges? They attract, perfect. Which means that one wants to go to him and he wants to go to there. And then these guys are going to attract towards each other. If we have attractions, what does that do to our boiling points? What does it do to our reactivities and stuff? It can make them sometimes more reactive. Generally, it makes them less reactive. But what's it going to do to our melting point? Yeah, it increases your melting points. So if you have, the stronger your forces are between different molecules, the higher it's going to, like, the harder it is to change its phase. Like, do you guys know what happens? Like, what it actually is between, like, remember the classic particle model. So let's go classic. Particle model of the phases, actually. So you've got your three containers. You've got your liquid. Oh, you got your solid. Actually, let's go liquid over here. No, I'm going to make that my gas, or else it's going to be confusing. You've got your gas here. You've got your liquid here. Then you've got your solid over here. If we look at these at like a molecular level, your gases are far away. Your liquids are kind of far away, but still pretty close. Then your solid, very tightly packed. What do we have to do to this one? So what do to melt? So what do we do to melt a solid? You heat it up. Good. What are you doing when you heat something? Yep, so good. You're disturbing the molecules, you're adding more energy into it. Temperature is literally just the vibration of molecules. The more a molecule is vibrating, the more it can like move around and the more energetic it is. And that means it's going to start to change its phase. Once we get to our liquid, how do we turn our liquid into a gas? We boil it. How do you boil something? You heat it up. Good. Which means that these molecules, which are already further apart than these ones, because they've got more energy and they're moving around more, now start to move around even more. Yeah. Of course you can. And then once you get to the gas, then if you add more temperature to them, you eventually get to a plasma, and then it just becomes ionized. So you lose all of the electrons that are hanging off. But all that we're doing here is you add more energy. Therefore, add more vibrations. So you add more vibrations to particles, which makes them separate. Making them separate. So if you add in more energy and then you make them vibrate more, and the more you make them vibrate, the more they separate, why do you think that having forces between them might increase your melting points of them? So if you add more energy to something, so you start off with your solid, you add energy to that, it begins to melt and it becomes a liquid. Yep. Then you add more energy to that. What happens to it? It becomes a gas because the particles do what? They vibrate more, and then they become a gas, which means they're further apart. So what is it about having stronger forces between our different molecules? Continue. Yeah, so it makes it harder to vibrate. Like if you hold everything really tightly together, it's really hard to make them separate from each other. If you have something that's non-polar, like is there anything really attracting the non-polar things together? Is there any electrostatic forces between them for non-polar molecules? That's the one like your chlorine and chlorine together. Is there any difference in the electronegativity between them? Yeah. That's for the non-polar. Yeah. So if I've got my non-polar, so I've got chlorine and chlorine, there's zero difference. So does that mean so they're going to be completely neutral, which means that they're not going to interact with anyone else? Which means it's really easy if you add a bit of heat to them. Like there's nothing really trying to hold them together, so they're just going to fly away. So these are generally our gases. So if we look around us all the time, we have oxygen in the air, we have carbon dioxide in the air, we have like hydrogen. Oh, we don't actually have much hydrogen. We have helium, we have heaps of nitrogen. All these different gases, they all have really low melting points, which is why they're a gas at room, like right now, at room temperature. It's because the molecules inside of them are they're holding themselves together. Like they're not holding themselves together, so they can just become a gas really easily. What is the most vital thing that you need for life? It's a liquid. What makes Earth unique in our solar system? We have water. What type of water, though? Liquid water. Good. So liquid water. So within liquid water there you have a polar molecule. So this one has a slight charge here and other slight charges down here. Because the water can be attracted to each other, and then you can have another water over here. This is actually a different type of charge, but you've got different types of charges holding between that. It means that water has a higher boiling point. So instead of it evaporating away at -40 like dry ice does, so carbon dioxide, water stays liquid, like well up to 100 degrees. So between 0 to 100, it's still in a liquid phase, which is really, really handy for us because it happens to be our planet. Generally doesn't go that much above and below 100 degrees, which means that we have liquid water on Earth. Not bad. Very handy coincidence. So that's what happens with water. So because we've got polar molecules, we can get some forces between them. In water, you have more of a thing called a hydrogen bond, but we're going to get to them later. So with our dipole-dipole forces, which is where we were before we got sidetracked, our dipole-dipoles, we have a little bit of a charge and we have a little bit of a charge. So they can attract together. They are going to raise the effect of the melting point and the boiling point. And it's going to be pretty significant, but it's not going to be like the biggest force of them. But these ones can increase. So dipole-dipole. Results in increase, melting, and boiling points. Even though the name is really annoying, the actual name itself tells you what's going on within it. So if I have my first molecule, I'm just going to do it as a big triangle because it's going to be easier. Slightly negative, slightly positive. Within this one molecule here, how many poles do I have? One. So I've got one pole over here, and I've got another pole over here. So I've got 2 poles. So just below that picture that you were colouring in before, Fox, with the highlighters. Has it come up? Okay. Yeah. So one positive, one negative is one pole each. And then if I put another one over here, how many poles does the second one have? If it's the identical molecule? 2. And then what's going to happen if I have 2 different molecules near each other that both have charges? They're going to attract each other. So you've got dipole, you've got one dipole molecule, and then you've got another dipole molecule. And then when they attract each other, you have a dipole-dipole force, because you've got 2 different molecules that have forces attracting each other. Yeah. So we're talking about one dipole molecule and another dipole molecule, and then you've even got the little hyphen to show how they're interacting with each other. Bam. All right. So our dispersion forces. So some covalent substances exist as a solid and liquids at room temperature. So things like our iodine, our bromine. Molecules such as these are neither ionic nor polar covalent, but they still have some forces of attraction holding them together. So these forces are called dispersion forces, and they result from temporary induced polarity within the molecules as a result of unequal or uneven electron distribution within atoms and between neighboring atoms and molecules. So whilst we don't have any permanent polarity at any time, the shared electrons may be closer to one atom than the other. So generally we get dispersion forces happening like within really big atoms or within like bigger atoms where we have an unequal distribution. Ooh, why does it do that? What has it done? Oh, yeah. Okay, so my pen wants to work again. All right, so just below the dipole, dispersion forces. So these generally happen. So generally, bigger atoms have these. And the electrons are temporarily more concentrated at one side or another. So you kind of end up having like a globby with your nucleus over here, and sometimes you have more over here. So more here, or more over here, or more over here. And as you have more and more electrons just in different places, they're going to start to make a little temporary dipole over here, or another temporary dipole over here, or another one over here. And then those ones are going to start attracting things together. These ones also, you have more, they get stronger as molecules get bigger, or molecular weight increases or gets bigger. When our molecular weights are getting bigger and stuff, does that mean that we're generally going to have more electrons and more protons? No. So if my atom gets bigger, does it generally mean that I have more protons and more electrons? Or like if it gets heavier? Yeah. Where are my lightest elements found? Where are my heavier ones? So, and are my ones further down generally bigger or smaller? And do they have more electrons or less electrons available? More. So if we have more electrons, which means we can move more around, we've also got bigger things around them, which means it makes it harder to just move that particular element. Like you need more energy to add into that one particular like atom to be able to make it move around more. So just waiting for the pen to come back. Okay. All right. So we have a sumo wrestling ring here. Over this side, we're going to have, who's going to be our little guy? Let's just use fluorine. And fluorine is going to be versin. It's going to be our iodine over here. Who do you think is going to be harder to move around? Iodine, because it's really big and heavy. So as he gets more mass or more weight, it's going to be harder to move him around. If it's harder to move around, what does that do to our melting points and boiling points? Yep, so that increases. Damn it. Harder to move around. Sorry, my pen's just decided to be annoying, like always. Can I draw with my finger? No. Foxsmith has left. Oh no. Okay. Looks like it stopped drawing for me for a sec. But yeah, as you add more weight to it, you're going to increase your melting point and you're going to increase your boiling points of them as well, because they're harder to move around, which means that they're going to be less energetic at all times. Let's keep going down. And then finally we get to hydrogen bond-in, which is the one that happens within water molecules. If I can get this to work again, I will keep drawing. If not, looks like I might just have to go to a chatty type one. No. Why do you do this to me? Always just... Oh. No. Okay. Looks like I've lost drawing ability for the moment. Huh? No, it's the actual pen. So the pen itself that I use to draw, it has a habit of just disconnecting or it just stops wanting to work. Generally, I take the battery out and it starts working again. But today, it's been particularly annoying. But yeah. Okay, so... Oh, we're back. Cool. Well, what have I done? What have I done? Whiteboard. Disappeared again. Alright. We are going to talk about hydrogen bonding. I won't be able to show you guys, but you do have notes that show it. So with your hydrogen bonding, we showed a picture of it up the top before. So your particular molecule, your like water molecule, you've got the oxygen, and then coming off at slight angles, doing like almost like a little triangle-y type thing, you've got the different hydrogen molecules coming off that. So each one of those is going to have a slight little dipole around them, and then those hydrogens happen to be really, really happy to make new bonds together. Hydrogen bonds are way stronger generally than your dipole, or some of your dipoles, which means that you can get quite a bit of attraction happening between different things, resulting in like being able to have good changes. And making sure that you can get like a decent boiling point and everything for them. So that's just the hydrogen, which has a highly electronegativity, being able to bond in together and do stuff. Cool. All right, looks like we're back for a sec. So with these, rub this out. So you have water. So just near the sumo wrestler. You'll have another water up here. Another over here. So these guys are all going to be attracted to each other. And they're all going to go through. And having like this lattice of attraction between everything means that you can get a fairly strong molecule forming from that. And then that means that water has quite a few strength. So yeah, you don't get a very big like dipole, but you do get a really good ability to be able to increase the general boiling point of it. Then last one was the bond strength and chemical properties. For this one, I'm just going to move down a little bit more. As we get stronger bonds between them, it's going to be harder. So this is just below the sumo wrestler. Get stronger. It is more difficult to have a chemical reaction, as chemical reactions are the result of bonds forming, actually bonds breaking, and reforming in new arrangements. So the stronger our bond is, the more difficult it is to break that bond in the first place. If we have a hard bond to break in the first place, it means it's going to be hard for it to be able to be very reactive. If we have a really, really easy bond to break apart, it means you can just like sneeze on it and the whole thing's just going to cause a reaction to take place, because those bonds are going to be broken and then they're going to try to get themselves back into a really stable formation or a more stable formation, resulting in a chemical reaction taking place. So generally our order for them is dispersion into dipole, to hydrogen, to ion network, and then finally at covalent networks. And a covalent network, that's something like a diamond, which is really unreactive. And I think that's the general gist of finishing off the term.